Um, yeah, so I have been already introduced, and what I will talk about is also summarized. So I don't need to talk a lot in this first slide, other than thanking everyone for attending for this webinar. So I worked with digital twins for quite some time now. I was thinking how many years ago I first started to work on digital twins, and I think it was 7 years ago. And I mainly worked creating digital twins of robots during my PhD. Um, so in this talk, I will talk about the foundations of digital twins, and then the architectures, perhaps from the computer scientist and roboticist perspective mainly. But then I also had the chance to be research associate at the University of Cambridge, and that was the time and first time that I involved with smart infrastructure and construction, civil engineering projects. In that sense, I wanted to touch upon the things from that experience, what it meant for a computer scientist, for someone who was trying to build digital twins for systems like robots, autonomous vehicles, and so on, coming into infrastructure, civil engineering domain, and trying to repeat the work. What does this mean and how it happens? And I will mention a few things from my experience and some of the studies that I did specifically for smart infrastructure domain. And the third part is about some industry reality check, I called it, because I had the chance to talk with people who are driving the biggest digital twin projects in the UK. And I asked them questions about digital twins and their approach. So it summarizes that. And the last part of this talk is about multi-agent systems. So what happens when we take a step back and not only focus on building a digital twin, one twin, but trying to coordinate multi-digital twins and how this can be done. Currently in my lab, we do this with robots. So I thought that if I can summarize that little bit, it can perhaps give you some inspiration and see how else digital twins can be used further. So what is a digital twin really? I was quite surprised when I first talked with people about digital twins, and I didn't know anything about building information modeling, BIM, and at all. So that was really interesting to see how people can define digital twins. The digital twin definition that I knew before coming into smart infrastructure and construction domain was the one that come from NASA, which is talking about multi-physics, multi-scale, probabilistic simulations mainly that uses the available physical models and sensor updates to mirror the life of the physical twin. In 2003, Greaves and Vickers said that it's a real space and a virtual space connected through data and information exchange. So they made something else out of it, actually. They didn't focus a lot about the physics of that. But they said that there is an exchange of data and information. So we call this feedback loops a lot in robotics and mechatronic systems. The center that I worked at the University of Cambridge was called Center for Digital Build Britain. They had to do their own definition, surely, and it was about the realistic representation of an asset, process, or a system in the built or natural environment. So this can show us how variable and it can be the definition of one terminology, and surely digital twin term is not the only one. You know, we have so many different terms at different fields, and people defines it completely differently. So I think this ambiguity and not having a one definition is not really the most important thing, rather than what it causes is important, because it shapes all the decisions that follows. So what you expect from digital twin, then this becomes your design decisions. I looked at different architectures of implemented digital twins in 2002. And that time there were only 13 digital twin implementations, research outputs that shared their architecture. And I looked at 4 different dimensions of this. Can it connect to other digital twins and assets? Because I am cyber physical systems person. And that was very futuristic to many. Only one was able to do that. Do components and external systems actually talk to each other? So is the components integrated in a digital twin? Several of them did that. So feedback loop between the physical and digital existed, but not all of them. Is information presented in human-centered way? So is this, what does this connection makes really? Why do you use the digital twins? Can you communicate what's happening to a user? And then does it do something beyond showing a picture of an asset? You know, like this is what is happening now, but then what? And that was also, unfortunately, not the case for all of the implementations. Sometimes people just wanted to have a digital twin, but then there was no services driven by that. The one that I liked, and then during my work in Cambridge, I used is called C2PS, and it has 5 layers. It starts with the physical layer, where we have the physical asset and infrastructure, and on the cyber layer, we can virtually design the counterpart of each physical thing, each part of this asset, and surely we need to collect data about it. It can be sensor data, surely, as NASA always thinks that it is, but it can be other type of data or as well. And again, most of the things stays here. So I have a physical asset, I built the digital twin, and then done. But actually, there are 3 more layers on top of that that one can talk about. It's relationships, so links between these two, and feedback loops. So when something changes in reality through the sensor data, you reflect this change on the digital counterpart, and vice versa. You can use this in the digital part and define an action and send it back to the physical layer. And then service layers, so many things can be driven from this. Data analytics, maintenance, operation related things. And then the interaction layer, where you let the user to not only see, like with visualizations, but also administer or manage the system through this user interface. Then the project that I worked in Cambridge is called a bridge, intersection bridge 5, it is called, which was a railway bridge in the UK. And the idea was building a digital twin of this. It was a 26.8 meter rail line, 2 lines, managed by Network Rail's Stafford Area Improvements Program. You will know much better than me about the structural specification and properties of this bridge, but it was reinforced concrete deck, and we used fiber optic sensors on it. And then the team was mainly construction structural engineers. I was developing software and doing data science. And then we were in contact with the network rails, asset managers, and so on, several stakeholders on that. It was interesting because most of these people never interacted with a person like me, and I never interacted with them. So it took us some time really to understand where we are coming from and what we are trying to do. So for the sensing, we use fiber optics, strain, temperature, accelerometers, cameras, laser rangefinder for detection, and humidity sensors. Then we use optical interrogators, microcontrollers, real-time embedded industrial controllers to control the data flow. And then we had a mini computer on site, then 5G network to transfer the files from this mini computer to the cloud. Then we did all the process and the presentation layer on top through this cloud platform, which provided structural analysis, statical final element models, and 3D model builder with a dashboard that the user was able to see what's going on. So the idea was like we sense, then we analyze, we visualize, and we enable the user to act. And these actions were mainly, I mean, if we like, you can sense the strain, temperature, displacement. You can analyze pre-stress loss, structural utilization, sometimes deterioration, and then visualize this in a meaningful way that the user can manage loading or get alerts on damage, even manage traffic and so on. But to come to there took us a lot of time really, because to me it was very important to understand why we are building a digital twin, which was not that clear to people who were structural engineers, because they didn't even know what was digital twin. So what you can do, what you should do. Sometimes what they wanted from me was just an analysis, and I didn't think that you need a digital twin for that. You can do that in MATLAB. You already do it in MATLAB. Why do you need a digital twin, you know? So I pushed them a lot to understand what's going on at the beginning. But then it paid off because we were then building a language to communicate and understand each other more easily. So this is the physical environment and all the components that I mentioned from the health monitoring, structural health monitoring aspect, and then the data acquisition, and then local and cloud data transfer. So even this figure took us lots of meetings to come up. But when I had them figured, then this architecture was done and everything was clear after that, you know. These kind of small things that different disciplines have different traditions and does things differently was really interesting and eye-opening for me to see. And this is how the bridge looks. On the cloud, the cyber architecture part, we did Docker containers running in parallel and we use entirely open source web-based architecture. These are some of the technologies which are not really important, but yeah, we wrote several papers about this also that you can find more details about the implementation. I think what is the most important part and what I remember most about this experience was the beyond one asset going to systems of systems perspective. And it was really difficult because we are talking about, even though digital twin is a digital twin, even though it is a bridge or robot, doesn't matter. Actually, so many things about these two assets are so different, and it matters a lot. A robot, is a real-time system that continuously collects data and lives very short time when compared with how long a bridge lives, right? Our robots are 10, 15 years and then done, but bridges can survive hundreds of years. So this time scale, the speed of the time was really interesting to work with. And then doing a digital twin of a robot for me was like, we do this for a specific reason, which then this digital twin will be connected to other things and so on. So I was pushing all the time the team to tell me, so what can we do with this digital twin? Can we help the asset managers to take decisions on traffic? Can we also measure the water quality under the bridge and say something about that? Can this bridge talk with other bridges? What happens with that? So we try to build the digital twin in a sense that it can be then connected, integrated to other digital twins. And the architecture that I told you at the beginning was actually these 5 layers, different things, different digital twins, and then integrating different data coming from all these network of systems, digital twins, and then building services and interaction layer on top of that. At the end, we come there, but I think it shows how different industries and domains are more mature and advanced in using the technology and creating the technology. So I hope it is not the case because I did this study like 4 or 5 years ago. So maybe now it is better. But the real possibilities and opportunities that this kind of technology bring was not really utilized or operationalized at that time. So at the end of this, I learned that designing a digital twin has different perspectives, and one is the system's perspective, to understand your own system, right? All the sensors, all the components, all the microcontrollers, and your data storage, and all these things. But also the further other digital twins and future possibilities that requires you to build your system in a way that can be integrated later to something else. Information perspective, like collecting the data. I mean, I was asking them how often do you want to connect this data? And at the beginning, it was like, yeah, we can collect it all the time. And I was like, fiber optic sensors, I never worked with them before, but the test that we did and the amount of data we get, I was like, how are we going to deal with that kind of a huge data set? And why would we do that? Especially when your asset lives 100 years. I understand for the robot to have sensor on all the time because the operation is all the time. But for the train, railway bridge, the train even pass there every minute, or like so many other dimensions about information and data comes to picture that needs to be also taken care. But to me, the most important part of this was the organizational perspective, to bring multidisciplinary teams together and build a vocabulary together, and then have managers or leaders in these teams that can bridge the gap between these different multidisciplinary stakeholders, developers and engineers in the team is really important. And generally, people don't see this part. But without this, I don't believe that a digital twin can be successful, really. Then the industrial reality was I talked with 9 executives. They are senior leaders across UK's infrastructure projects and building digital twins in these projects uh, for city, water, transport, and energy sector. They were doing big multi-year long projects, both building these infrastructural assets, but also at the same time building digital twins. So I asked them several things, which makes us go back to the first slide where I asked what is a digital twin. And even there, 9 people 9 different answers. And some said that it's when physics influenced the digital and vice versa, simply the feedback loops that we talked a bit. And some said that no, digital twins don't need to have a real-time performance or even feedback loops. So then there was also a lot of discussion about what is a 3D or CAD file that represents the represent digitally the design of the physical asset. Are they digital twins or not? Or is BIM a digital twin or not? We talk about it a lot. And most of them really said that no, they are not. So there was something that they thought that the digital twin needs to be alive, but the level of granularity of how alive and how these feedback loops needs to work was really very diverse. And I was asking them why do they want to have a digital twin, and they gave me quite good answers. To be honest, I was like, okay, people understand the value out of this, even though they imagine different products. At the end, what value they want to get out of this was much more aligned. And then we talk about what are the barriers. Why cannot we have digital twins in every project, every asset? Why? And I think the main three areas of barriers was like the technology adoption. I put some of the codes, what they have said here. Some talked about like that, yeah, we have a data, but it is very poor quality, so it doesn't really gives us anything. Some talk about the culture. Sometimes I want to drive these things as an executive, but at the end of the day, I need someone in the ground to do something which they don't understand why they should do. So we should be able to explain this to people, and that takes time. And some also talked about the skill sets that not everyone is really have the necessary skills to do this. Especially building a digital twin is a quite complicated, big. Not one person can, not one person project. It needs to be a team. And then we also discussed a lot, like getting a really talented computer scientist or data scientist to work in this project. You need to offer something that big tech companies cannot offer. So your competition becomes completely something else now. And these are also some structural changes that the whole discipline needs to go through, which again takes time. So we focused on the barriers and how this can be, and we built 3 strategies. Surely one is the digital transformation, giving organizations room to experiment and not always be successful. Sometimes some projects might fail, but they learn a lot. And in technology companies, actually, this is very common. The cultural transformation, which is again about clarifying the goals, communicating with people openly, and building accountability, making people embrace and feel belonging to this decision. And then bridging the skills gap, which is again very structural, but investing in training and education of current workforce and partnerships, and making the sector a bit more competitive so you can employ data fluent talent similar and can compete with other tech oriented disciplines and domains. And before concluding, I will talk a bit about what I do today and what can actually digital twins do. I think that it is a bit a step more than creating a dashboard which reflects and have feedback loops or with the physical asset. Today I do multi-agent systems, and then we do active coordination and learning for autonomous agents. In our case, generally robots, and I will show you a bit more in few slides how they look like. But this layer architecture, 5-layer architecture that I told you, is not that different really. It's the idea, the fundamental architecture is the same. So we have a physical layer, we have a cyber layer, we make it possible for different agents to coordinate and communicate with each other in different ways. And then we allow them to do things together. And then we shape this collaboration, we call it, in different ways. And though these are all fully autonomous systems, we always have human in the loop. So we have oversight, dashboard, and also ability to engage and control the robots whenever it is necessary. Mm. A bit different than what we have in smart infrastructure. In robotics, especially in multi-robot systems, we have some challenges because things happen very fast, and then we need to arrange ourselves, or the robots need to arrange themselves according to other robots. And this is not only arranging by location, but their actions and policies needs to be reshaped also. Um, some of these open challenges are partial observability, we call it, which means that like um, i- i- we never believe that we have all the information. We always observe things partially because the sensors are noisy, occlusions can happen, environment changes very fast. So every decision that we make it under uncertainty, and dealing with partial observability is one of the core challenges that we look. Then our world is not static. Um, because it is multi-agent system, all the agents constantly make decisions and take actions, and we don't have all the information about all the agents. We don't even want to have that. So this constantly changing dynamic, non-stationary part is also very challenging. And then it's a bit different than digital AI. In physical AI, we cannot reverse things. If a robot cannot catch what it needs to catch, then there is a harm there. We have critical safety issues and so on. It's not like a GPT AI, digital AI platform hallucinating, giving you wrong answers, and then tolerating this. It doesn't work in our reality. And then surely the coordination of these multi-agent systems, that when everything is dynamic, constantly changing, and we only observe it partially, where everything comes together, it becomes really complex problem. At the same time, I will go a bit fast because I think, yeah, I have 5 more minutes, but I will go a bit faster for the last part. Yeah, at the same time, while we have these complex open challenges, we also have very interesting solutions existing all around us, actually, because nature also operates in very similar open challenges. For instance, bees navigate and forage, and they don't have a GPS. We have GPS, which is really powerful. What bees have is much more simplified than that, and still it works. Or ecosystems co-evolves consistently and continuously. Um, People, praise and predators adapt to each other's strategies consistently, but no one issues an update patch. Um, Organisms evolve under permanent and irreversible consequences. Like biological risk taking is an incredible thing to really study, especially if someone is working on safety in engineered systems, because it is calibrated so finely that irreversibility is the main driver of how these risks are calculated and calibrated. And surely multi-agent coordination exists, and not only in swarm like collectives, but also trees share nutritions with fungi, and later the fungi shares their nutritions with the trees. They communicate, and collaborate. They do different logistics and managing different actions and coordinating things together. Um, so this gives us a lot of examples where we can try to imitate. And this is exactly what my lab does. These are the robots that we have in the lab, and these are the simulations that we use. Sometimes we use high fidelity digital twins and simulate them, very much like physics informed, and works with real constraints and limitations of physics. But sometimes for us, it is not only about the physics of the digital twin, but mainly the intelligence part of it. Then we don't need to complicate things, but by getting a high fidelity simulations, so we simplify things like this one. And this is also another thing that we talked a bit about digital twins. Sometimes you don't need high fidelity CAD designs if you are not really interested to see what is going on. But if you are really looking at the structural change of a crack, then you need to take photo of the crack in different times, and this is like very data heavy. So depending on really what you want to get out of your digital twin, it matters a lot how you make the design decisions. And it comes back to my experience where I was pushing people to give me answers. Why do you need a digital twin, and not getting the right answers, because the answers they were giving me were not digital twin implementation. They needed something else. So this understanding and aligning about the development of the digital twin is really important. But when you do this, then what you can do on top of this, for instance, this is one of the studies that we published this year, and here we look at the multi-agent, different type of robots collaborate to fulfill some logistics-related tasks. This is a warehouse, and they need to collaborate actions together to go to same place, and robotic arm takes the package and puts it in an AGV, for instance. So it is different embodiments, gives the robots different abilities. If you are a robotic arm on a mobile robot, you can pick and you can take a package from a shelf, for instance, but you don't have a space to carry it, so you need a picker to come, another mobile robot to carry this. So these scenarios are not really the most important thing. The important part of it is that different embodiments, different shape of bodies and abilities and functions makes the problem a bit more complicated when we talk about, for instance, heterogeneous multi-robot systems. And here we use symbiosis that exists in the nature as an example. And we find out that we complete as many tasks without the symbiosis, but we balance the resources better and we complete the tasks faster by just having this symbiosis relationship between. But more than that, when we complicate the scenario more and more, the benefit increases more. So this is really interesting, interesting finding. So one can after having digital twins, to try different scenarios and use the power of AI to do things better and faster and see the difference. And these, because we use reinforcement learning, the agents, even though we didn't tell them how they should, for instance, balance their workloads, they did that by themselves after the training. And the most interesting was that they specialized, which is what happens in the nature also. Some of them choose to carry big boxes only to increase their rewards. Some of them took the long distance package deliveries and so on. So it also gives a lot of interesting emergent behaviors to analyze at the end. And then another study we did rewiring and multiplasticity, which happens in our brain. It's an incredible mechanism that makes us to remember and forget things. So it was, we simply try to see what if we make the agents to remember each other and do things together. And if they are not doing, to not really concentrate remembering and saving the data and just forget them and look for new relationships. I mean, we did this in a more hierarchical and complicated way, but what we get inspiration from multiplasticity was that we used like 4 plasticity rules, but I'm not going to go in that detail on that. The interesting thing was that this algorithm achieved 9600% of the same performance, where we have agents that knows everything about all the other agents, which in reality we never built this kind of system. It is so complicated, so data heavy, very costly. But that's the best thing. You know, if you know that, then you can take your decision very well calibrated way. We only use the 15% of that all information in the links, and we were still better, especially when we disturbed the system, um, made some faults or moved the packages from one side to the other side. The system was 3 times more resilient. It was very fast to come back also than the other compared algorithms and systems. So these results are all published, and I am very grateful for all my PhDs and postdocs who always takes the challenge to go my wild ideas. So I want to thank all of them for this. But where does this take us? So if we make the digital twins like common every time possible product, that everything that we build have a digital twin, then we can have simulations, then we can build this data analytics, we can look at the feedback loops, then we can embed AI in different forms, for our case, reinforcement learning, but there are so many other ways of dealing with this also. And this gives us more resilient systems that absorb the failures, that can reorganize, that can take actions themselves. Certainly increases the efficiency. These systems can specialize, they can cooperate and coordinate actions by themselves. And also we can get advantage of different positive emergent behaviors that they can later becomes able to by themselves decide and take actions on. So this was what I planned to say today. I would like to thank you everyone again, and yeah, and if you have any questions, I am ready to answer.